Combustion. It's the fiery heart behind engines, power plants, and even rocket launches. But what exactly happens when something burns? In this video, we will dive into the science of combustion, where chemistry meets heat and motion. How a tiny spark turns fuel and air into energy. We'll break it all down into a simple visual way. So buckle up. Let's ignite our understanding of how fire really works. In this video, we will discuss what is combustion, reactions, efficiency in combustion, types of combustion, combustion equations, combustion models, and CFDLAND products. Combustion has been used in every aspect of human's life from very beginning. For lighting, when you light a candle, a torch, or an oil lamp. For cooking and heating our houses. For industrial burners, rockets, and for our cars. There are even natural incidents like wildfire that happens in jungles. But how a fire forms? Combustion is a high temperature exothermic redox chemical reaction between a fuel and an oxidant, usually atmospheric oxygen, that produces oxidized, often gaseous products in a mixture termed as smoke. To light a fire, you need oxygen, fuel, and heat, that is, the ignition energy. After you gave the external heat, then combustion happens, and the heat released helps the combustion to continue. But if you need to have another form of combustion, like explosion, our triangle turns into a pentagon. You need two more conditions. Dispersion of dust. Dust is our fuel and oxidant. Dispersion means how well they are mixed together, okay? We need them to be mixed into each other. And confinement of dust. We need the dust to be bounded by walls. We need it to be in a closed chamber. And redox means there's a transfer of electrons. Oxidizer, oxygen, accepts electrons, and our fuel, usually hydrocarbons, donate electrons. So, the most common reactions in combustion are the reactions of hydrocarbons with oxygen, that they produce carbon dioxide, water, heat, and light. Of course, there can be other forms of fuels like this reaction, where we have hydrogen as our fuel. As you can see, the product of this reaction is only water. Makes it a perfect reaction for emission-free usages. So this reaction and its reverse, where you use water as a fuel to have oxygen and hydrogen, are studied by scientists to use it in our everyday life. We have methane as the simplest hydrocarbon, reacting with oxygen, producing carbon dioxide, water, and some energy. The last reaction is the Octane's reaction. So gasoline, a very common fuel, is a mixture of hydrocarbons, but it is mostly made of octane. And as you can see, it produces the highest amount of energy. As you notice, there is only water and carbon dioxide in our products, making all these reactions stoichiometric reactions, meaning that the fuel and oxygen are in exact proportion. We have maximum heat release and highest possible efficiency. Different parameters affect and influence efficiency in combustion, including fuel composition, fuel to oxygen ratio, temperature, pressure, mixing quality, flame shape, and stability. For the temperature, for example, if the temperature is too high, we will have byproducts called nitrogen oxides. So some energy is used to form these byproducts, and this keep it from forming carbon dioxide and the right products. It causes to form carbon monoxide. If you look at the plot here, as you go to right, we have excess air, and as you go to left, we have air deficiency or excess fuel. When we have excess fuel, we have carbon monoxide because there is not enough oxygen to form carbon dioxide. And when we have excess air, efficiency decreases. We have the best efficiency when we have stoichiometric combustion reaction. And as you can see, as the oxygen increase, carbon monoxide decrease. The reactions are not always so direct. It's not like that we have the reactants at the left side and they directly change to products, carbon dioxide and water. Sometimes there is a chain of reactions. First, the reactants change into something else, and after that, after some more reactions, they turn into carbon dioxide and water. This causes to have many byproducts like carbon monoxide, like nitrogen oxide, like soot, and they all affect efficiency. There are different types of combustion. We have complete combustion, that is when we have carbon dioxide and water as our products. They are the only products we have. We have incomplete combustion, that is we have byproducts, our emissions. It could be due excess fuel or excess air. We have spontaneous combustion that is dangerous in environments where highly flammable materials are present, like coal, oil, or other things. We have rapid combustion, that is like burning LPG, liquid petroleum gas, in our gas stoves, the ones you use for cooking. We have explosive combustion, well, firecrackers is an example of explosive combustion. We have smoldering or slow combustion. Well, when you light a cigarette, you have a slow combustion. And at the end, we have flameless combustion. Well, there are some benefits to flameless combustion. There is lower amount of nitrogen oxides. They have higher efficiency, and heat distribution is uniform. Like many fluid flow problems, the governing equations for combustion problems include Navier-Stokes equations, that means continuity, and momentum equations. But two more equations are also solved in combustion problems: energy equation and species equation. In the species equation, we have a convection term, that is the transmission of chemical species as a result of the bulk motion of the fluid. And we have the diffusion term, which means a move from high concentration to a low concentration area. And if our flow is laminar, diffusion term is calculated like this. And if it's turbulent, we compute it with this equation. Now we are going to discuss the combustion models used in ANSYS Fluent to simulate combustion problems. To simulate combustion in ANSYS Fluent, all you need to do is to go to Setup section, click on Models, and then go to Species. When you click on a species, a box opens for you. And as you can see, under this model section, you have different models like species transport, non-premixed combustion, premixed combustion, partially premixed combustion, and composition PDF transport. These are the models that you can use to simulate your combustion. We're going to discuss each model in details in just a few moments. Species transport is one of the most fundamental and widely used approaches. This model allows users to include both premixed and non-premixed combustion, model finite rate chemistry, and simulate complex phenomena such as pollutant formation or incomplete combustion. One of its major advantages is flexibility. Users can define any chemical mechanisms, couple it with turbulence models, and integrate effects such as radiation, evaporation, or heat release. It's also computationally efficient compared to detailed chemistry or flamelet models when used with global reaction mechanisms. However, the species transport model also has some limitations. Because it directly solves conservation equations for each species, it becomes computationally expensive as the number of species or reactions increase. It can struggle to capture thin flame fronts or detailed flame structure in high speed or highly turbulent flames unless combined with advanced submodels. Additionally, it assumes continuum diffusion and may not represent microscale mixing accurately. Then you can choose reaction, volumetric. You can also check wall surface or particle surface or electrochemical depending on your problem. So for example, wall surface considers reactions that happen at the wall. Then in the mixture material, we choose our species, both reactants and products. The selected database mixture material, including all species and properties, are copied to your case and appear under mixture in the tree and the material task page. If any properties are missing, the solver prints a notice of the required data. Then we can choose the turbulence chemistry interaction. The first one is finite rate, no TCI, no turbulence chemistry interactions. It computes only the Arrhenius rate and neglect turbulent chemistry interactions. It is good for laminar flows and turbulent flows using complex chemistry. That is, turbulence timescales are faster compared to the chemistry timescales, or the chemistry is highly complex. Then we have finite rate eddy dissipation. In this model, it computes both Arrhenius rate and mixing rate and choose the smaller between the two. In eddy dissipation, it only computes mixing rate, and eddy dissipation concept models turbulence chemistry interaction with detailed chemical mechanism using submodels. These submodels are constant coefficient and partially stirred reactors. For our chemistry solver, if it is non-direct source, it means it is good for density-based solver. If you have a finite rate problem, choose Chemkin or Steve solver. And when you have pressure-based solver, choose stiff or relaxed solver. Here you can see the contours for mass fractions of oxygen, methane, and hydrogen. These contours are plotted using species transport model. The next model that we are going to discuss is the non-premixed combustion model. As its name says, fuel and oxidizer enter combustion chamber from two separate streams, and mixing occurs by a combination of turbulent stirring of the fuel and oxidizer streams and molecular diffusion. Under certain assumptions, thermochemistry can be reduced to a single parameter, the mixture fraction. The mixture fraction is the local mass fraction of burnt and unburnt fuel stream elements in all the species. Atomic elements are conserved, so mixture fraction is a conserved scalar quantity. Then governing transport equation does not have a source term, and it helps us to simplify the combustion problem to a mixing problem. This model was specifically developed for the simulation of turbulent diffusion flames with fast chemistry. It allows for intermediate species prediction, dissociation effects, and rigorous turbulence chemistry coupling. It is also computationally efficient because it doesn't require the solution of a large number of species transport equations, but it requires the flow to be turbulent, and chemical kinetics must be rapid so that the flow is near chemical equilibrium. This kind of combustion is used for furnaces, internal combustion engines, and pool fires. The next one is the opposite of non-premixed model. is premixed model. It means that the fuel and oxidizer mix at the molecular level prior to ignition before they enter combustion chamber. Combustion occurs as a flame front propagating into the unburned reactants. For example, you can see this kind of combustion in aspirated internal combustion engines, lean premixed gas turbine combustors, and gas leak explosions. This model is more difficult to model than non-premixed model. The premixed combustion usually occurs as a thin propagating flame that is stretched and contorted by turbulence. For subsonic flows, the rate of propagation of the flame is determined by both the laminar flame speed and the turbulent eddies. The laminar flame speed is determined by the rate that species and heat diffuse upstream into the reactants and burn. Practical laminar flame thickness are very small, of the order of millimeter, so resolution required are usually unaffordable. The limitations of this model is that it must use a pressure-based solver. It is valid only for turbulent and subsonic flows. It cannot be used in conjunction with the pollutant models and cannot use it to simulate reacting discrete phase particles. Here we have a simulation in open foam that shows temperature for the flame. The next model is partially premixed combustion. So in this model, fuel and oxidizer already mixed in together enter the combustion chamber from one stream, and from a separate stream, oxidizer or fuel is also injected into the combustion chamber. So partially premixed combustion is a premixed flames with non-uniform fuel oxidizer mixture. Behind the flame front, the mixture is burned and the equilibrium or laminar flamelet mixture fraction solution is used. Ahead of the flame front, the species mass fraction, temperature, and density are calculated from the mixed but unburned mixture fraction. Within the flame, a linear combination of the unburned and burned mixture is used. The underlying theory, assumptions, and limitations of the non-premixed and premixed models apply directly to the partially premixed model. Again, here we have a partially premixed combustion, and we can see the temperature changes. In these areas, we have the highest temperature, and these areas, the lowest. And the last model, composition PDF transport. It is used when we are interested in simulating finite rate chemical kinetic effects in turbulent reacting flows. With appropriate chemical mechanism, kinetically controlled species such as CO, carbon monoxide, and nitrogen oxides, as well as flame extinctions and ignition can be predicted. This method is computationally expensive, and it is better to start with small grid and preferably in 2 dimensions. Another limitation of this model is that it is only used for pressure-based solvers. And discretization in this method is in 2 methods, Lagrangian and Eulerian. That the Lagrangian one is more accurate, but needs more time to converge. These are the results for a study that used PDF model, experimental results, and another model for jet flow. As you can see, for here we have the temperature and mass fraction for fuel and oxidizer. As you can see, the PDF model is in a good agreement with experimental results. CFDLAND offers numerous solved projects in combustion category. All the projects can be categorized into 5 groups. 1. Industrial and equipment combustion systems. 2. Chemical reaction modeling and reforming processes. 3. Non-partially premixed and spray combustions. 4. Unsteady, pulsating, and acoustic combustion. 5. Specialized, hybrid, and erosion heat phenomena. To access these projects, just go to our website, cfdland.com, CFD Shop, Engineering Field, and Combustion. You can check all our projects. To see more, just click Load More. And you can get access to more projects. For example, Selective Catalytic Reduction System CFD Simulation with wall film and multi-component DPM is a chemical reaction modeling and reforming process project. Or Wet Coal Combustion CFD, DMP combustion particle, is a specialized hybrid and erosion heat phenomena. When you click View Details, you will have a thorough description of what the problem is, what is the phenomena, and how it is simulated with ANSYS Fluent. The process is explained in details, and what result you can expect. You can order the solution, and you can have additional offers like you can ask for the geometry and mesh training videos. The file for geometry and mesh will be given to you when you order this project, but you can have the training video too. If you still have questions, you can ask for an online training meeting, and you can also have case and data files. Pretty amazing how something as simple as fire powers everything from engines to rockets, right? Combustion is more than just flames. It's chemistry, physics, and engineering, all working together. If you found this video interesting, don't forget to like, subscribe, and check our website for numerous projects. Thanks for watching, and keep the curiosity burning.